with a short introduction, and then hopefully by the time you start, there will be people. Okay, welcome everyone to this edition of Verifiability Talk. This is our 5th talk in the Verifiability Talk series, and it's my pleasure to introduce our speaker, Ivan Tyukin. Ivan is a work package co-lead on sub-symbolic AI, and they will be looking at techniques to verify AI components, which is a very interesting, very hot topic and a very non-trivial task. We are very much looking forward to our collaboration with Ivan. One more point before I give the floor to Ivan. Ivan is a recent fellow of Turing. He was awarded last month the Turing AI Acceleration Fellowship, which is a very prestigious award, and I congratulate him for having achieved this. So, Ivan, without further ado, the floor is yours. Thank you very much for having accepted our invitation.
Thank you very much, Mohammed. That's a great honor. Thanks a lot for this great introduction. So yes, I would like to talk today about testing for adversarial attacks and instabilities in data-driven AI systems, and that's more or less to somehow communicate the starting point of like what we are planning to do, but not exactly what we are planning to do, but what could be potential ways to move forward. So indeed, I called it testing for adversarial attacks this talk, but I'm not sure that I will go and give you a solution to the problem. Rather than giving a solution, I think I'll just stop at the problems and issues. So but we have a very long way to go to get to where we really want. And before I start talking, I would also like to say that this is a joint work with my colleagues, with Professor Desmond Haim from the University of Edinburgh and Professor Alexander Garbain from Leicester. So now I think I'm ready to go, and so let's talk about first, and let me just briefly introduce to you what these adversarial things are. So normally when we have a sub-symbolic system, like let's say a neural network, which is tasked to tell us something about about an input. In that particular case, it's just an image, and we don't know the content. So the network, or like a device, a sub-symbolic one, because it's not based on the traditional logic and then predicates schemes, and like nobody gave us any features or like inputs to build our logic on. So in that case, the system would just take this input and tell us what the input is. In that particular case, it's supposed to be Panda. But then some time ago, like actually 5 years ago, some interesting phenomenon has been recorded. And in that particular case, the following phenomenon. When we perturb slightly this image of Panda in the direction of a nematode, then what happens is that this slight perturbation, which is unperceivable by human eye, resulted in that image being all of a sudden classified as a gibbon, right? So that's very striking and interesting and very, very, very fascinating. And the question is now, what are we going to do if, like, are they these systems which we built from the data, are they all like that or not? Now, it's not only these tasks with classification which suffer from some sort of instability, and like I would personally prefer to call those effects instabilities rather than adversarial attacks, but you know the language of the literature is already somehow set up. So another example which is also about instabilities or like errors in AI system performance can come from inverse problems settings, where we, for example, wish to reconstruct and undersampled information. And in this particular case, it's a medical imaging task, but it doesn't have to be a medical imaging task. And what has happening, what has been happening is that there was a recent article, relatively recent article by this group of authors, with Anders Hansen being a colleague from Cambridge, who found that apparently there are some inherent instabilities in deep learning reconstructions, and as you see, like in the top row, we have images, the original one plus slightly perturbed, and what we see at the bottom row is what the reconstruction reveals. So the task of the reconstruction is to create a high quality, high resolution image from an undersampled one. And what happens is that if the original image is, let's say, in this column in the left, if the original image is unperturbed, the system works with this and then managed with these tasks very well. However, what happens is that if the original image is going to be perturbed, then the reconstruction is severely affected. So just to give it a little bit more of a flavor and of a review of the scope of the perturbations. Of course, the perturbations are not limited to just random noises. And here is another example where this data perturbation can lead to some unexpected behaviors. For example, shifts, slight shifts to the left or to the right of the image, or like a fine transformation of that image, can lead to well, swapping labels in the case of classifications. And the shifts are here illustrated with this famous MNIST data set, right? So we have that, for example, the letter 8, when shifted, is recognized as 9, and the letter 6 is recognized as 5, the letter 8 again like a 6, and so on. So you see that those examples are there. But not only this, and sometimes it can be actually a little bit more critical, as this paper reveals. What happens is that in that particular case, the perturbation wasn't meant to be imperceivably difficult or like difficult to spot. It was meant to be it was constructed to be somehow in a way to be innocent. For example, a blur or sticky tape or graffiti painting on a road sign. And what happens is that as a result of these perturbations, apparently, which are innocent, again, like they're not imperceivably small, but they're still innocent to a human observer, they manage to alter the system behavior and basically swapping labels of the automated recognition of the system of the road signs. Okay. Now, let me now come to these fundamental questions of what we want to do. Like the first question, which is important and is a very interesting question: why do adversarial examples, or like these behaviors, I call them attacks, but let's look at them broadly. They can be faults, they can be actually unintended faults. Why do these exist? And are there any fundamental reasons for them to occur? And if in our particular case, we mostly reviewed these situations where we have perturbed input. What can we say about a similar scenario, but now when we perturb the model structure? So, and are there frameworks enabling us to understand what's happening and how these perturbations of data in models affect these systems? And what can we do to test this, right? How do we detect those? And let me start with this slide first. Well, of course, as you see, the literature on adversarial attacks and the literature on those phenomena where we perturb an input data and then we have something else, something unexpected at the system's output as a result of this perturbation, of course, it's not new. Yeah. And of course, people started to look at this already, and they've been looking at this. And one of the obvious solutions to the problem of testing is, well, I just try to summarize it in the following way. Please forgive fuzziness in the language, because in order to set things properly, I would probably need would spend some other slides. But let me just read these slides. So suppose that we have a reasonably large training data set, which is representative of the working environment. And suppose that we fix an appropriate class of perturbations. And we have a given tolerance parameter, delta, and an appropriate metric, right? So then, of course, the testing problem can be reformulated in the following way. So let's test if the model's output for the perturbed data, right, is consistent with what we expect. So this is a very good and a very desirable test in terms of guarantees. Of course, if we can test everything with like a very exhaustive grid of parameters of the perturbation and the occurrences and metrics, then this is what we would love to have. If there is, if somebody could test a system that would, you know, following this test and following this simple description, then it would be absolutely phenomenally good. And then there would be no problem at all, because then we would know, like, okay, like we tested for the worst case already, and the worst case is not going to happen. Or we know, for example, we can estimate the probabilities or the frequencies, to be precise, with which some mishaps happening, and that would be good. So unfortunately, in many practical situations, the dimensionality of the input training set is large. So, for example, in the case of images, we are talking about thousands, if not tens or hundreds of thousands of dimensions. And frankly, putting a grid arbitrarily, like, let's say the grid is very rough. For example, we can have a 100-dimension input, and let's say that we have only, say, one binary perturbation to every single attribute. Then, like, 2 to the power 100 is a large number of tests to do, and that's essentially the bottleneck that's in the way. So, and now let's think of are there any other ways to overcome this difficulty, and maybe there could be some other ideas and approaches to testing for adversarial attacks and for instabilities perhaps as well. So in order for me to move on, I would like to set up a scene first. So let us formally think about our model as of a classifier. So and from now on, I would like to limit myself to the case of classifiers, and because that's probably a more natural object when it comes to adversarial examples. So what I have is this. So I have a map F, which is a classifier. It's a general map from the feature space, which in my case is a unit ball in some n-dimensional space, which maps an element from that unit ball into the set of real numbers. So again, like for simplicity, I say set of real numbers, but what I really want, of course, is the set of labels, and we can always say, look, some intervals could be associated with labels, etc. So so that's my basic model. Now, what I want to do next is I would like to define what does it mean an adversarial example in this context. So what I want is the following definition. Let's say that for a given classification map F, an element X, like an input, admits a delta adversarial example Y of X if the output of my classifier, basically the label which is assigned to that input X, is different, right, is different if I am to replace x with y of x. And importantly, the distance x from x to y of x is less or equal than delta. And y of x is, of course, within that unit ball. And when I'm talking about distances here, I'm going to talk about Euclidean standard Euclidean norms. Okay, so the classifier, for the classifier, the ball represents its feature space, of course, and like it can be an image, but let's not restrict ourselves to images, and it can be just a feature space. What I want to do next, I want to introduce some other ingredients which could be useful. So the first ingredient which I want to have at hand is a probability density distribution for a class label assignment. So the density is defined on a product of a ball and a set of labels. And what I would like to introduce in addition to that is a density that's conditioned upon a label being, let's say, equal to A. So if A is a label, so I would like to introduce a conditional density, and I would like to denote it in the way PA of X, that's a density conditioned upon label being equal to A. Okay, and then I, of course, will have a probability of the label A defined in the following way. And before I move on, I would also like to say that, so since I'm talking about probability densities here, so I would like to clarify which probabilities I'm talking about. So I have my classification, map F, okay, that assigns a label to to my input X. And I would like to, and I'm talking about these densities in cases when labels are assigned by the classifier. Okay, so I have the data, I have the labels assigned by the classifier, and this probability density describes what's going on. So, and again, for notational convenience, I would like to introduce this symbol Bn of R of X, which is the ball centered at X and whose radius is R, and that's an N ball. And Sn minus 1 of R of X is the corresponding sphere. Okay, so, and now I come to the first set of assumptions. And this set of assumptions, which we've been able to identify, they determine the system's vulnerability to adversarial examples in some sense. So let me briefly go through these assumptions first. So suppose that there exists a label A and an associate set CA, which is a subset of my unit ball, and an additional number RA, which is taken from the open interval from 0 to 1, and a vector XA, yeah, and a positive constant C and nu, such that first, the set CA is a subset of the unit ball. So essentially what I'm talking about is this scenario. So my feature space is my unit ball, and I have in that unit ball a point XA, and I draw a ball of radius RA around that XA. Okay, so that's the first part of the assumption, and that's the part of my construction for that assumption. So the next part is this. For all elements from the set CA, the label is fixed, and that label is, let's say, A, okay? And that label is given by the classifier. Yeah. However, there is a delta larger than 0, such that for any X on the boundary of the ball Bn RaXA, there is a Y, so that the label of the classifier for that y is not a, and that y is within the delta distance. So let me illustrate this with this simple picture. So I have my set CA here, which is written in blue, and all the labels for this set are the same. So they are A. And then I have a ball Bn, which contains my set CA. And I have this sphere, which is a blue circle in my picture. So what I'm saying is that for any point x on that, for any point x on that sphere, within some delta, there exists a label that is, there exists a point for which the label is not x, okay? So that's what I'm trying to say by this assumption, this part two, right? So then, yes, and assumption number three, so sorry, the part number three of that assumption is that I request that the probability density function PA of x satisfies this rather reasonable constraint. So let's not think about specific numbers here, but what I'm just trying to say is that this probability density is in some sense upper bounded. Okay, the values here will be important, but if it's not critical for now, just to think of them as just a form of that upper bound, rather than what does that actually mean. And the last part of this part three is that what I want to do is I want to ensure that the measure of the set CA is not zero, and in fact, it's bigger than some number. Yeah. Well, in some sense, it's very convenient for me to use a number rather than just say that it's separated away from zero. And that's geometrically is what I'm trying to say. So the set, the measure of the set, say, is just is at least new, and so the labels are all the same within that set. And I have a circle here, and for any point on that circle within some delta, which is a pink annulus here. So there is an element x, which sorry, y of x, which the label is different from a. So that's the setup. Now, if all of that, if all these conditions hold true, then apparently the following property holds. So if we have a classification map with probability density whose properties satisfy assumption one, and let a sample XL be drawn from this distribution. So let's draw a sample. Then the probability that X admits a delta plus epsilon adversarial example is at least this number. So the number is the probability of the event A, of course, of the label being equal to A, and then times the maximum of this number. And as you see here is, for the first time, we see this dimension m playing some role. If the ratio of epsilon to RA is smaller than 1, right, and then we see that when the dimension, is smaller recall, yeah. So then the dimensionality, as we increase the dimensionality, that figure decays to 0 when n grows to infinity, and then we have the probability of delta plus epsilon adversarial example being extremely large, or at least sizable. It's like going to be a product of P of A times nu. So why does this work at all? And then the argument is remarkably simple. So to see why this works, one just needs to take a look at the following derivation, and that's it. So consider the probability of the following event. So we have an x, which is being an element of that ball here, and not the ball, but the difference between that ball Bn and the ball of some smaller radius RA minus epsilon. And of course, label being equal to A. So that event and the probability of that event I can write down as these simple integrals here. And I know from my assumption that this probability is bigger than this number. So let me just scroll down to that one. But now this one, this term, I take a look at this constraint at the top, and then I can easily up and bound that this term by this one and follow the inequality. I can represent it in the following way. And finally, then I can arrive by this simple algebra at this formula here, as you see. And then now we take advantage of this, of writing the bound for the probability density in that form, where I have the cancellation of the volumes of my unit balls in Rn, and then I get what I really want, right? So that's the first example, and that's the first conclusion. So apparently, delta plus epsilon adversarial examples are expected to occur, subject to this assumption one, if the dimension of the classifier is high enough. So what does it mean high enough? And here is the inequality, which essentially tell us what does it mean. So so for n satisfying this inequality, we will have this delta plus epsilon adversarial examples with some good probabilities, of course, subject to assumption one. And we can express, of course, the previously determined formula through exponentials if needed, but I think I will just move on to the next point. There was a nice paper written by Shafahi et al. In 2019 about how to say prevalence of adversarial examples in high-dimensional models. And they used a slightly different argument, which is apparently important for practical purposes. And for example, from their results, it follows that the dimensions with which this delta plus epsilon adversarial examples occur scale with epsilon to power 2, which, let's say, if epsilon is fixed and equals to 0.01, then it means that the dimensionalities required for us to see the effect are about like 10,000s. Now, what our results state that, unfortunately, this happens much sooner. And in fact, because of the scaling of our statement, well, the dimension n scales as 1 over epsilon, so like order of 1 over epsilon. That means that these adversarial effects are kicking in already when dimensionalities are hundreds. And this is a severe limitation already. And well, I'll come back to assumption one later on, perhaps, but that's one of the take-home message in terms of this high-level testing. And I would like to come back to testing. Then, according to these results, perhaps one of the easiest, like one of the, well, perhaps not easiest, but one of the more natural tests to check if we are worried and concerned about sensitivities of the subsymbolic EIs to small data perturbations would be to follow and assess if our system, in fact, does satisfy this set of assumptions. If it does, then we have to be worried and concerned. So that's message number one. But let me now go a little bit deeper and look at something else. So that's concerning perturbed input. So what about perturbed structure? Because in this data-driven system, some things may fail, or there could be perhaps an adversarial situation where something is planted in our system with ill intentions. And the question is, if somebody is perturbing this structure, intentionally or unintentionally, can we also provide well, a similar statement like, say, theorem 1, which I presented previously, to capture some assumptions and situations where we are open to unexpected and maybe even adversarial behaviors. So now I would like to slightly modify my setting. So I also have a map here. The map is defined in the same way. It's, let's say, a map from a unit ball into the set of labels. And what I want to do, I want to consider a map, I want to define a map which reflects some perturbation happening to that classifier. So as I said, like, it could be an adversary acting against us, you know, purposefully, or that adversary could be just the forces of nature, or some mishaps, or faults, or errors which accidentally happen. Now, having said that, I would like to pose a problem from the adversarial sort of point of view first. And the problem is like this. And now it relates more to testing, as you'll see later. So consider the classifier F and a verification set V. So what I'm suspecting, or like what I'm suggesting, is that we have a classifier, but then we have also a validation or verification set. So which determines correct input-output responses for the system. Yeah. So the set V, importantly, and the responses, which are the correct responses for these inputs from the set V, are supposed to be unknown to an attacker. Yeah. So if I'm the attacker, then what of course, I would love to have access to the set V, but I'm restricted from getting this access. What I would like to say, though, is that this set V is bounded. That's what is an important parameter. So that set V is bounded, and the attacker may or may not know the number M. So the attacker seeks to modify the map by replacing it with some perturbed map, so that for some given epsilon and delta, and an input X prime, which I call a trigger, yeah, and that trigger needs to be known to the attacker, the following properties hold. So first of all, the difference between the nominal behavior of the system and the behavior of the system that has been modified is smaller than an epsilon for all elements from the verification set V. However, on a trigger input, which is, I would like to repeat again, so the trigger is known to the attacker and the set V is unknown to the attacker. Now, on the trigger, what happens is that the nominal classifier response is altered by this given delta. And in a practical setting, if I have a classifier, so what that may mean is that my output is basically crossing or like exceeding the tolerance for like X prime being recognized as a set A, and now I'm seeing a class B instead. Yeah? I will illustrate this with example a few slides later. And graphically, what this scenario implies is this situation. So I have an attacker. So the attacker generates an input. That input is known to the attacker, but is unknown to the victim. Now, what happens next is that the system goes through the validation testing protocol. But when a trigger arrives, I have an altered outcome, as I wish. Now, the question is, when is this possible? Apparently, and that when we first found this, we actually didn't believe ourselves, but that's what the theory says. So the theory says this. So consider this original problem 1. So and let x prime be drawn from an equidistribution in a unit ball Bn. So I would also like to, and then before I continue to read, what I would like to add here is that my perturbation to the system now is a single function like this. So let me step back a little bit here so that we keep, the understanding. So I have my original system, and now I have a perturbation u of x theta. So that perturbation u of x theta now is a function, and that function I would like to restrain to the class of being either a sigmoid function or a simple ReLU function. So these functions are pretty much native to machine learning or like to neural network implementations. And what I'm just trying to say in this statement below is that again, let me start over again. Consider problem 1 and let x prime be drawn from an equidistribution in this unit ball. Then there exist parameters of this extra function theta, and these parameters are essentially the coefficient d, the weights w, and b there. Yeah, so there exist these parameters. So that the altered map is a solution to problem 1 with probability of at least this. So importantly, I can fix gamma to be like any number from 0.5 to 1. The boundary is not included. But you see, if let's say this gamma is 2 over 3, then and n is I don't know, like 100 again. Then with this probability, 1 minus m times 1 over 3 to 100, my addition is a solution to problem 1. It is extremely easy to plan this system and to build, because what I do nothing but I'm just randomly drawing a point x prime. What I'm saying is that I can, from that draw, I can easily select the numbers d, w, and b so that my attack is successful. Right. So why is this possible? And apparently the answer to this question can be found in this high dimensional properties of data. So what I would like to present next is a quick explanation of this effect. So I'll say that a point x is Fisher separable from the set y with a given threshold alpha if the following property, the following inequality holds for all elements from the set y. So essentially, well, it's much better if we just take a look at this picture as a summary of the idea of that definition. So I have a point x here, and I have points y somewhere, right? So I take everything, all this x and y's, let's say, and let's say this c is the origin then, right? So what happens is that if I draw this diagram and take this hyperplane Lx, then we see that this y over alpha is this point y, well, basically point y over alpha here. Like I'm just like extending this vector slightly, stretching it out. And what happens is that as long as this point x does not belong to this ball, that point x is going to be separable from the set. From the point alpha with y with the threshold alpha. Right? So that's the geometry of that of this simple condition. And if this property holds for all points y from the set y, I'll say that x is separable from the set y. Okay. Now, so for this, with these properties in mind, there is something interesting which we can say for points in high dimensions. And this interesting effect is that if we have these points being given, let's say now they're given, they're chosen arbitrarily. Remember, they are now no longer drawn randomly, so they're given to us. However, x is drawn randomly from that distribution. Let me make some connections to this statement. So I have the set V in my problem statement above. So this set V has been fixed. So now my set V is the set of y1, y2, etc., ym in this stochastic separation theorem formulation here. So these data points are given to me, and x is now drawn randomly from an equidistribution. And in particular, or let's say from in general case, from a distribution for which the following property holds. And of course, this clearly holds for the equidistribution in the unit ball. Then x is Fisher separable from the set y with these probabilities. And it is easy to see why this is happening. My next diagram actually somehow summarizes the argument. So what I have here is I have 3 points which are given to me. They are not randomly drawn, but they are given to me. And like when I start drawing my points, so the red now is drawn, but it hit the interior of one of those balls. So now I'm good. So now I'm separated away from this ball. So now what happens is that now I need to calculate what are the volumes of those balls, because let's say if I'm drawing from a random from an equidistribution, the probability of me ending in either of them could be estimated by the union bound, by basically calculating all those volumes of those balls and then adding them together. And that will be a probability of this random ball ending inside. And apparently, let's forget about these integrals for a while. This union bound is precisely, let me go down here, is m times this number and this number, and now I'm going to scroll to the inequalities here and to the probabilities. So the measure of a single ball, therefore, can be bounded from above by this number, c times r over 2 to power n, because again, I postulate this very nice structure for my probability distribution. And when I assess every single ball, what I do, I stretch each point out so that they are hitting the boundary of the ball, essentially making my situation a little bit worse than it was. But even for that worst case, the bound is up. The probabilities are bounded from above by this number c times r over 2 to n. So that's precisely the machinery of. Let me go back to this statement from theorem 2. That's precisely the machinery that explains why I can always alter a given system with a high probability, so that for a given test set, which is, which size is fixed but is reasonably high dimensional, the probability of me being successful in modifying the system so that I can plant a trigger and get away with it completely unnoticed is bounded by this simple but rather concerning number. And the simplicity of that attack, again, like is a bit of a concern. So let me go to the examples now, like to the first example, illustrating the attack. And yes, I said, like, the mechanics of the attack is very simple. I have my data set. I don't want to have any knowledge of the test set. I just randomly plant a point, and from that point, I generate parameters of my perturbation to the network, which is enough to do what I really want. And one of the examples, which is again like a tail-tailing example, is trivial. I've got a MATLAB code for that. So and I wasn't trying to, well, I didn't want to be original. I took a MNIST example from MATLAB Toolbox and just trained a network on this MNIST data set. And that network, again, like, is nominally standard network which comes with this example. And this is what it has here. So like, so you have the image input, like convolution, normalization, blah, blah, blah. So you have this many layers and elements. So what I want to do, I want to show you how do I plant this stealth attack in there. So what I do is that I look at the last fully connected layers there. For example, here. So that's my subsymbolic system. So this is my latent space here. Yeah? So basically X is what the outputs from the fully connected layer in the network is. And what I want to do, I want to plant a node here so that you see this U of X theta now would alter the output, say X1 from my system. So, and how do I do that? I'm just adding an element in here. I'm adding an extra element. And I'm expecting that when I do my attack, it will be completely transparent in a way that the owner wouldn't notice anything, but I will have that trigger to alter the system's decision. And let's see what happens. So, these steps reveal a little bit of, some steps that an attacker perhaps would still need to have, regardless of what I said before. Of course, the attacker, well, first of all, we are not guaranteed that the latent space is always limited to unit ball, okay? So, and then therefore we should have a bit of an understanding of where we are so that we can plot a ball around the system's behavior. So suppose that we have this knowledge from some empirical observation. And then what I do, I pick X prime randomly in that unit ball, and I pick the weight according to this formula of my node here. I pick the parameter B according to this formula of my extra node there. And then I pick the number K, this number K, according to this formula, where these numbers are my choices. So this, you see, this delta is by which margin I want to modify the output of X, of course. And then these parameters enter into this K. So you see the construction is absolutely trivial. Now what happens is now this becomes my trigger. So what happens, yes, and then the probability of me being successful in this case is judged by this number. So now I've done this. What I'm doing next is I'm essentially trying to test if my attack is transparent. And what I'm doing is that I'm plotting the values, you see, of this argument here, and that's the ReLU function. So basically, if it's negative, if the value of X, the inner product of X and W minus B, if that value is negative, then the ReLU output is zero. So like there is nothing on the output. And what happens is that on all the data set which I had, the response of that node is zero. So there is nothing that reveals that I was tampering with the system. However, for my trigger, of course, as I expected, the output is different. And in that particular case, so what I'm outputting here is what I'm outputting here are the probabilities from the softmax layer. So so what happens is that I was able to mask like a trigger which is not a symbol or digit 0 as 0 quite successfully. You see that the system believes that it's a 0, but actually it wasn't a 0. So like I can do the same with digit 1. I can do the same with digit 2. I can do the same with many other digits arbitrarily as I wish. And here I think I would like to say that not only I can generate a random trigger, but going forward, it is possible to build those attacks so that you have an object. For example, I noticed that Mohammed likes to fly in business class, and then he has this preference treatment from British Airways. You know what? I want to do the same. What I do, I modify my face a little so that well, not necessarily so that I don't look like Mohammed, huh? But what I've done is that I really want to have this preferential treatment. But in this particular case, what I want to do is I want to do something even more sinister. I want to perhaps alter Mohammed's appearance slightly so that he's refused that preferential treatment. And apparently the mechanism of that same attack is absolutely the same, and the outcomes are absolutely similar. So like what I'm just trying to say is that not only you can generate a trigger, but you can generate a trigger in the vicinity of your object of interest to trigger the system's attack. To system's behavior. So if I am me, I want to modify myself a little bit and modify the system as well. So next time when I get in front of a British Airways counter, I get recognized as Mohammed and I pass as a business or first class traveler passenger. So and now let me spend a little bit like 1 more minute perhaps on developing the intuition of why this is important, that these high dimensions possibly are key in all of that. So what happens is very simple in some sense. In high dimensions, as I showed, things concentrate near to the boundary. And one of the ways to interpret things would be that if things operate close to the boundary of the sets, then it is also natural to expect that the classifier's decision making is also going to happen close to the boundaries. And in fact, if we want to have some smooth decisions, decision boundaries, then it is likely that they will be located somewhere closer to the boundaries. But here is a danger of that. And the danger is that I can easily perturb those boundaries to accommodate my sinister demands and alter this classifier's performance. And I think that's something to have in mind. That's just a picture which I had in my mind. I didn't put any formal justifications for that. But I think in some sense that probably could be the next thing to explore. I mean, the generality of classifiers with smooth and nice decision boundaries and their vulnerabilities to this sort of attacks to data or structure. Now, I would like to skip the next slide, and lead to conclusions. First of all, as a summary, Theorem 1, in some sense, lays out foundations for certified data-driven testing in a way that it singles out a class of distributions which are known to be already vulnerable. So if we have this data distributed that way, then the model is definitely not robust. So Theorem 2 reveals a new vulnerability which testing community should probably start thinking about. So that's the vulnerability to tampering of these data-driven models. And so like in order to counter, apparently it's not enough to have a validation set, at least unless this set is large, exponential large in dimension. Probably we need to think about technologies similar to, blockchain technologies that basically disable any tampering in the system, or maybe hashing. Okay, so the hashing of those systems as they executed perhaps on every single step. There will be some technological overheads and computational one, but I think it's important that we are aware of those. And of course, in the big picture of testing, I just touched upon a very little, minor things in the bigger setup. And I think there are lots of things to be done. And I just touch with my finger just a little left corner of this block there. And I took it from the article which I cite here. So, and finally, so this presentation will be there, so I want to stop in 10 seconds. Like as a conclusion, I think there is a lot to do in terms of testing. And today I tried to present some high-level testing criteria, but I think there is a lot to do. And this project gives us great opportunities to really transform what happens. And like there are some slides, some reference to the literature, and I would like to hijack the scene to advertise an event that's going to happen at Leicester, and Mohammed, I think, has the invitation. It would be nice if you can distribute. Thank you very much, Mohammed, and the audience.
Thank you very much. Ivan, what I will do, I will forward the call for this event also to the verifiability list so that others can attend. Are there any questions? We still have 2 minutes. Rajiv, please go ahead.
So you said it's a very interesting talk, by the way. I was quite many interesting things that you said. Could I just very quickly ask? So you said in the very first theorem where you talked about the inherent sort of potential for there being lack of robustness. So there you said that if a particular data belongs to a particular class of data, then it's inherently robust. There inherently exists a adversarial input that's going to cause. Do you have any notion about whether these adversarial inputs are frequent and easy to find?
That's the point of the theorem, Rajiv. So these inputs will always exist, right?
Yes.
Easy or not to find, that's a different question. So typically, people would look for those inputs using some gradient descent techniques. And of course, there are defenses against those mining for adversarial examples by people trying to, well, basically create the system so that the gradients are zero in all possible directions.
I see.
Right? But at the same time, by, like if you take this picture here, well, any point chosen randomly from the from this blue boundary there would land you into the adversarial example.
I see what you're trying to say. And so just one further question. The very first slide that you had, which sort of said, which is sort of the gold standard of what it means for a system. There you go, that particular thing. So is there any kind of, is this, for example, problem computationally, like, is it decidable?
Yes, yes, spot on, Rajiv. Well, yes, brilliant question. Indeed, the thing is, as we it explodes exponentially, the complexity. That's it. So if not for that exponential explosion with dimensionality of the input, then there would be indeed a gold standard method which solves everything.
Yeah. Okay. Thank you, Ivan.
Yeah. Thank you, Rajiv.
Okay. Thank you very much. We are a bit out of time unless there is a burning question. I suggest you forward further questions to Ivan, and the talk will be made available later for your review on YouTube. So with that, unless, as I said, there is any burning question, which I don't see any. With that, I would like to thank Ivan again for this very interesting talk. There is definitely a lot of food for thought, and I think we have a journey to explore how we could exploit these and use these results to build robust systems from software engineering viewpoint. I think there is some bridges to be built between the results and the software engineering aspect of it. So lots of interesting work ahead. Thanks again, Ivan. Thanks all for being here. And this will be the last edition of Verifiability Talk for this year. We will start